Good morning to all. So,
Good morning, sir.
last time we were discussing about the rearrangement reaction. There we have seen two reactions. One is pinacol rearrangement, and other is the Wagner-Merwin rearrangement reaction. So let us see the next reaction, next rearrangement reaction. That is the Baeyer Villiger rearrangement reaction. It is also called as a Baeyer Villiger oxidation reaction. So let us see next reaction, Baeyer Villiger oxidation reaction. So this is the third reaction that we are taking in this topic. The name of this rearrangement is Baeyer Villiger rearrangement reaction. Rearrangement reaction. So what is this reaction? So in this reaction, what happened? The starting compound is a carbonyl compound. The starting compound is a carbonyl compound, that is RC double bond O R. R may be same, may be different. The reaction takes place in the presence of per acid. In the presence of per acid, we'll see what is meant by per acid, and it is observed that there is the introduction of the oxygen between the RC bond, and it will convert into corresponding ester RC double bond O R dash. So the starting compound is a carbonyl compound, either aldehyde or ketone, maybe open chain or maybe cyclic, and it will convert into corresponding ester. So you are getting ester, and starting compound is the carbonyl compound, right? And this per acid, what is per acid? Uno acid, not uno acid. So acids can be represented like this one, RC double bond O and OH is called as acid. Example, if H is, it is a formic acid. If Re is a CS3, it is acetic acid. Similarly, benzoic acid like this one. And per acid means here per acid means you have to just add oxygen in between oxygen and hydrogen, right? So you are getting one more extra oxygen, RC double bond O and H. So it is called as a per acid. It is also written like this one, RCO. Here how many oxygens are there? There are 3 oxygen, 1 2 3. So CO3H, right? CO3H. So it is called as a per acid, right? It is called as a per acid. Okay, so here you have to see the examples of this per acid. Just depending upon this acid, you have to write its a name. For example, if it is a HC double bond O and OH, the corresponding acid is a formic acid. So it is called as a performic acid. It is called as a performic acid. Why? Because we put oxygen in between the oxygen and the sulfur. If suppose if you take acetic acid, CS3C double bond O, then O, and here there's the H. So again you add one oxygen and here you put H. So it is called as a per acetic acid. Per acetic acid. So simple name, just you have to put the word per before that acid. If it is a benzoic acid, right? If there is a benzoic acid, so here there is a benzoic acid, pi bond, pi bond, pi bond. There is a C double bond O and O, and here is the H. It is called as a benzoic acid. Benzoic acid, right? So it is called as a benzoic acid. And suppose if I add one more oxygen, in this case, if I add one more oxygen, then it is called as perbenzoic acid. Here we put one more oxygen, so it is called as perbenzoic acid. Suppose if I put on the meta position or para position, suppose there is a Cl, right? There is a Cl, then it is called as a metachloroperbenzoic acid, and metachloroperbenzoic acid. So here metachloroperbenzoic acid. So in this way we can use the number of per acids. So you know the now per acid. Now how the conversion takes place? What is the mechanism of this reaction? As we add oxygen on this carbonyl compound, that is aldehyde or ketone, so it is also called as a Baeyer Villiger oxidation reaction. And as there is a rearrangement takes place, so it is also called as a Baeyer Villiger oxidation reaction. Let us see what is the mechanism of this reaction. Mechanism is also very simple. So let us see the mechanism of the reaction. Mechanism of this reaction. So in mechanism, suppose the starting compound is your carbonyl compound. So here is R, C double bond O and R dash, that carbonyl compound. This carbonyl compound, when you treat with per acid, here the per acid is this one, H. Here is a, just I will write arrow, right? So the per acid is H O O C double bond O and R. So this R may be same or may be different. Now this sigma bond will open on this oxygen. This sigma bond will open on this oxygen. Oxygen get negative and H get positive. So this H positive, it undergo protonation. You know the oxygen have the two lone pair. One of the lone pair form a bond with this H positive, right? And there is a formation of a protonation of this oxygen. So here you can write like this one. C, here is R, here is R, here is a double bond, oxygen. One of the lone pair form a bond, so oxygen carries positive charge. Oxygen carries positive charge, right? Now, as oxygen carries positive charge, we have to neutralize. So this sigma bond will open on the oxygen, and the negative from this reagent, that is O negative, here is O, here is the C double bond O and R, right? And R. Here is the R. R may be same, may be different. So what happens? It will attack on the oxygen. Pi bond open on the oxygen. There is a neutralization of the positive charge, as oxygen have two lone pair. One of the lone pair is involved into the formation of bond. As pi bond open on the oxygen, there is a neutralization of the positive charge and it regains its lone pair. At the same time, this carbon carries positive charge. And now here, this negative will attack on the C positive, and this negative will attack on this C positive, and you can get a bond with this carbon and oxygen. So I will write the same thing, right? So here there is a C, there is a carbon, here is OH, oxygen regain its lone pair. So I can write this two lone pair here also, and remaining part as it is. Here I can write R and R, maybe same, maybe different. And the oxygen from this per acid attack here O, here is O, here is a C double bond O and R. So per acid will attack here. Now further, there is a rearrangement takes place. So in this case, there is a rearrangement takes place, and how it undergo rearrangement, that is an important step. So here what happens? Oxygen is a more electron. Here is a nearer to the CO. So this sigma bond will open on the oxygen. This sigma bond open on the oxygen. O becomes negative and this O becomes positive. You know that this oxygen cannot be positive. So what happens? R along with electron pair. R along with electron pair means either I have to put the tail of the arrow on this bond, or I have to take a circle with containing a bond. Right? So I will put the tail of the arrow on this bond, means R along with electron pair, it attack on this oxygen, means R negative. As soon as, or you can say this sigma bond open on the R negative attack on this O positive. As it open on the R, this carbon becomes positive. We have to neutralize this positive. So this one pair will shift here, and there is a formation of a double bond, right? So you can get corresponding rearrangement step. So what happened in this case? Here we introduce the oxygen atom. So I will write down the same thing here. Here is R as it is, and on this one there is an attack of oxygen. There is an attack of oxygen. So here is a O also, and remaining part as it is, right? Remaining part as it is. So this will shift here, right? This will shift here, and this C becomes C double bond O and R, right? So this lone pair, they are involved into delocalization. So oxygen carries, that is the positive charge. This oxygen carries positive charge, right? Now in the next step, what happens? In the next step, we have to remove H plus. There is a deprotonation. There is a removal of a proton. Deprotonation takes place. How? This sigma bond will open on the oxygen, neutralization of the positive charge, and oxygen regain its lone pair. So you are getting such type of product, and you are having R, right? It undergo rearrangement. This oxygen is coming from your that is a per acid, and remaining part as it is C double bond O and R, right? So in this way, it gives corresponding ester. It gives corresponding ester. So this is the conversion of, that is the carbonyl compound into ester. So this is the conversion of a carbonyl compound into the ester. So this is the conversion of a carbonyl compound into esters. So this is a very simple mechanism of this reaction, right? And you are getting corresponding product. And this H positive form, it may also react with this O negative, and also there is a formation of a byproduct, that is this H and this O form a bond, and you are getting H. Here is a O, here is a C double bond O and R, means acid. So the main product is the ester, right? So in this way, you have seen the mechanism. Also, mechanisms are very simple. The carbonyl compound will convert into corresponding ester. Example, just you replace the R by the methyl, you get the another example, right? So if both are alkyl group, they are same, then in that case you are getting the corresponding product, right? So we have right to shift any R group. If both are same, then you can shift any group. But again, if both alkyl group they are different, so again look here, we are going to attack the R group on the O positive, right? Means here you should attack on the O positive, means positive center. So R, which is a more nucleophilic in nature, it will attack on the oxygen. So if R alkyl group they are different, in that case the R group is found to be more nucleophilic in nature, it will attack and you can get corresponding product, right? Here in this case, suppose if I write the same example, if the starting compound oxygen is labeled oxygen, means O18, if it is O18, it is the isotope of oxygen, so it is observed that the oxygen which is found in the ester, it is also O18, means the CO group again it is from your carbonyl compound, the CO group is from your carbonyl compound. So here is your, that is the mechanism of the reaction. Now example I will write, suppose RR they are methyl, or RR they are the phenyl. Just you have to write down the same mechanism, but only you have to write the methyl or phenyl and phenyl, and methyl or phenyl and phenyl. Okay, so that we have learned already, right, in the generalization. Now suppose if I write another example, for example, next example. So just firstly I'll correct the example and then we'll go for the some other type of the mechanism. So in generalization we can say that suppose the starting compound is CS3 C double bond O and CS3, it undergo reaction with per acid. What is the per acid? In this case the per acid is, suppose it is a formic acid or acetic acid. CS3 C double bond O, here is the O, and here is the H, right? So what you have to do, we have to put only oxygen between the carbonyl carbon and methyl group, so you get the corresponding product, right? So the compound that you are getting is CS3, here is the C double bond O, here is the oxygen, here is the CH3, means carbonyl compound will convert into corresponding product. So this is example number suppose 2. Okay, now next example, suppose instead of methyl, if I put benzene nucleus, C6H5 benzene nucleus, or you can take pH for benzene nucleus. So C double bond O, and here is also pH. So again we can take the there is a per acid. Suppose if I take a formic acid, HC double bond O, here is O and H, it is a formic acid. You put one more oxygen, so it becomes a performic acid. And what happens? We introduce oxygen between the carbonyl carbon and benzene nucleus. So you are getting here pH C double bond O, here is O and here is a pH, means it will convert into corresponding ester, right? It will convert into corresponding ester. So in this way we can take the number of example when both alkyl group they are the same. Now next example, suppose you are having a such type of example. Suppose if there is cyclic compound, if there is a cyclic compound, or we take first the same compound, but if alkyl group they are different. For example, if there is a benzene nucleus, here is a benzene nucleus, right? Pi bond, here is a C double bond O. Also there is a benzene nucleus, right? Also there is a benzene nucleus. here is a pi bond, and pi bond, and at para position. Para position means here, and at para position there is a methoxy group, right? Methoxy group. So you know that as there is a presence of a methoxy group, it is an electron donating group. It exhibit plus R effect. It exhibit plus R effect. So when the reaction takes place, right? When the reaction takes place, in this case, wait just for 1 minute. Yes, hello, hello.
Excuse me, sir. Your mic is off, sir. Sir, you are not audible, sir.
Now, can I audible to you? Yes. Okay. Thank you. Thank you.
Yes, sir. Yes.
Okay. So here, what you do? Now I have taken the different peracid. You can take in general also, and you can take also in particular also. In general or in particular also. Okay. So here, just we have to wait for 1 minute. Just I will put power supply. Okay. So here you can take any peracid, right? Now I will take a different peracid. Suppose it is your acetic acid. It is called as a peracetic acid. Suppose hydrogen atom, if I have replaced by the fluorine, okay, so it will call it as a CF3, CF3, then CO3, I can write CO3H, right? CO3H. So trifluoroacetic acid. So it is called as a trifluoro because it is acetic acid, right? So I have replaced hydrogen by the fluorine. So it is called as a trifluoroacetic acid. As it is a peracid, so it is called as a trifluoroacetic acid. So we have to shift the R which is found to be more nucleophilic, means you have to introduce the oxygen which is more nucleophilic, right? So what you should get in this case, you should get such type of the compound. Now here is the pH, right? Here is the C double bond O, and we have to put here oxygen. We have to put here oxygen, and this benzene nucleus where there was OCS3, it undergo migration. It undergo migration means you have to find out which R group undergo migration. Then remaining part becomes easy. Okay, so again the mechanism is same as we have written in the above. You have to write down the same mechanism. You have to write down the same mechanism. So it is called as a migratory aptitude that you have learned in the pinnacle rearrangement reaction. So what is the migratory aptitude in this one? Here the migratory aptitude in the this reaction, that is called as a Baeyer Villiger oxidation. Here I will write the sequence only for some of the R group. So it is called as a migratory aptitude. Migratory aptitude. So first migration takes place if suppose if there is a aryl group. If there is a aryl group, right? If there is a aryl group, it undergo migration. Then tertiary alkyl group, right? 3 degree tertiary alkyl group. Then secondary alkyl group, then primary alkyl group. Why? Because in tertiary alkyl group, the alkyl group, there are the 3 R group. These are the electron donating group. That's why the electron density is more. More the electron density, easier the attack on the O positive. Then we can write the in substituted benzene, right? So these are for the alkyl group, and in the substituted benzene, just I'll write on the next page of the migratory aptitude. For example, which found to be more nucleophilic in nature. For example, here is the P at para position. There is a methoxy group. There is a methoxy group in the C6H4. C6H4 means on the benzene nucleus at para position there is a methoxy group. You know, methoxy group is an electron, that is the donating group, which exhibit OCH3. Oxygen have 2 lone pair, and here it is at para position. So here it is an electron donating group. It exhibit plus R effect. That's why it is a more electron rich when at a para position. It exhibits plus R, and you know the plus R is more powerful than the plus I. Suppose instead of methoxy group at para position, if there is a methyl, Me or methyl, again same thing, there is a C6H4. But in this case, what happened? Only there is a methyl group, and it exhibit only plus I effect, CH3. So it is an electron donating group. So you have to try yourself for such type of substituent, and you have to check which is a more electron rich out of this 2R, and you have to migrate that alkyl group on the oxygen atom. So without writing the mechanism also, we can write corresponding final product. Okay. Similarly, if it is suppose at meta position, the methyl group is at a meta position. You know, at when it is at a methyl group is at a meta position, there is no hyperconjugation effect. The hyperconjugation effect is possible at ortho and para position, but it's not possible at the meta position. So it is not so powerful. That's why it is a less as compared to previous. Similarly, C6H5, and we have seen the C6H5 other sequence. Similarly, if suppose these are the electron donating group, but if there is an electron withdrawing group, for example, that is at para position in the benzene nucleus. If there is a Cl, if there is a chlorine, chlorine exhibit plus R. At the same time, it also exhibit minus I effect, minus I effect. That's why it is less as compared to this one, and it is less, or it is a powerful as compared to when the methoxy group is at ortho position, right? It is at ortho position, OCH3. Oxygen exhibit plus R, but at the same time it also exhibit minus I effect. So in this way, we can write such type of migration aptitude in the Baeyer Villiger oxidation. So here what you have to remember? You have to remember that if two R group they are different, in that case the R which is a more nucleophilic in nature, which have the more electron density, it will migrate on the O positive, and there is a formation of a corresponding, that is the ester molecule, right? There is a formation of corresponding ester molecule, right? So here we have seen such type of migration in this compound, right? So same thing we have observed in case of pinacol-pinacolon rearrangement reaction, right? Pinacol-pinacolon rearrangement reaction, right? Now, if suppose we are having such type of moiety, if the CO group is a part of a ring, it is a very important and very interesting example. Suppose next example is suppose if you are having the firstly again I will take the one more example for this one. You are having such type of R, means cyclopropene, and here is the C double bond O, and here you are having a that is a benzene nucleus. You are having benzene nucleus, pi bond, pi bond, pi bond. Okay. So in this case, we have to check which is a more nucleophilic in nature. It undergo reaction in the presence of per acid. So of course, you know the benzene is found to be more nucleophilic. It is more electron rich as compared to cyclopropane, cyclobutane, like this one. That's why it will migrate on this one, and you are getting corresponding compound. It is the cyclopropane. Here is a C double bond O. Here is oxygen, and here is your benzene nucleus. Right? Here is the benzene nucleus. Right? So in this way, you have seen the some examples. Now, suppose if you are having the part of CO in the ring, very interesting example. They may ask in exam also. Suppose you are having such type of example, right? The reaction takes place in the presence of peracid. You can take any peracid, and for example, here we can write metachloroperbenzoic acid, or simply say acetic acid, or in simply say in general RC double bond O and H. It is your peracid in general. Now look here. Here is the carbon, right? Here is the carbon, and here is also carbon. So we have to introduce oxygen between the carbonyl carbon and the carbon. So it is a 5-membered, now it becomes a 6-membered. It becomes a 6-membered. So you are getting such type of compound, C double bond O. Here is also there is a formation of such type of a cyclic ester, right? Such type of cyclic ester. It is your cyclopentanone, it is a ketone, and it is called as here is the carbon alpha, then beta, then gamma, and delta. The size of ring is this one, delta. lactone, delta lactone. The cyclic ester, they are called as a lactone. Cyclic ester, they are called as a lactone, and this you have learned in the second year in the topic carbohydrate. So in the topic carbohydrate, there is a formation of a such type of ring, cyclic ring, when there is a conversion of a lower member into the higher members takes place. So it is called as the Kilani-Fischer synthesis. Kilani-Fischer synthesis, the conversion of the lower member into the higher members. So the one of the steps that there is a formation of such type of cyclic ester is called as a lactone, and depending upon the size of ring, it is called as there is a gamma lactone, and you get such type of a gamma lactone. So here I think I will write its the mechanism. So again, the mechanism is also very simple. So here you are having acid H, here is O, here is O, here is C double bond O, and here is R. Oxygen have the 2 lone pair, right? Oxygen have 2 lone pair. I will write this lone pair like this one lone pair and your 2 lone pair, right? So here what you can do, either you open like this one. You are having a different type of the possibility. So this sigma bond will, the reaction takes place in the presence of acid. So here what happen, this sigma bond, oxygen have the 2 lone pair. The lone pair undergo protonation. It undergo protonation to give such type of product, right? So here, just here is a carbonyl compound. Okay, carbonyl compound, and you are having a double bond. Here is O, here is a H, and one of the lone pair is involved into formation of bond. That's why oxygen carries positive charge, right? And in the next step, what happen? This oxygen, right? This oxygen will form a bond with this carbon. So pi bond open on the oxygen, pi bond open on the oxygen, neutralization of the positive charge, carbon becomes positive, this positive and this O negative will attack, right? So I can write like this one. This sigma bond means I will write here, here is a H, here is a H, right? Here is a O, here is a O, here is a C double bond O R in general, and this sigma bond having the lone pair, it form a bond on this carbon. So this lone pair will attack, right? This lone pair will attack. Okay, so we can write like this one also. This sigma bond will open on the oxygen, O negative, and this C positive, and you can get such type of the compound. So here you may get cyclic structure, right? Cyclic structure. Then here is the oxygen, here is the H. Why? Because there is a neutralization of the positive charge. The oxygen regain its lone pair. At the same time, the O from this per acid will attack, and you are getting a such type of compound. Okay. Now next step is a rearrangement step. Next step is a rearrangement step. What happen? This sigma bond open on the oxygen, O negative and O positive, right? O negative and O positive. So this sigma bond will open a bond between this carbon and this carbon. As it open and form a bond with this oxygen, so this carbon becomes positive. So this lone pair, they are involved into delocalization, and there is a formation of double bond. Again, I will repeat here, right? So what happen? Here you are having cyclic ring, that is a cyclopentanone in this case. So this sigma bond open, right? This sigma bond open. So just I will open this bond, right? This, or first I will write the skeleton, and then we'll write how it open and form a bond. Okay. So here there is O, there is H, oxygen having the 2 lone pair. Okay, then you are having, here is O, here is O, and here is a C double bond O and R. Same thing I have written. Now this sigma bond open here means O becomes negative. Just I will write here O negative means this bond is open. Oxygen becomes positive, right? As open, there is a formation of a negative, O negative, right? O negative. At the same time, this oxygen becomes positive. As oxygen becomes positive, the bond between this carbon and this oxygen, it will break. So the bond between this carbon and this oxygen, it will break, and this bond will attack on this oxygen. So I have to write a bond between this oxygen and this carbon, right? On this carbon. So there's a formation of bond between this one. So what is the size of ring? The size of ring becomes 6 member. It was a 5 member, it becomes a 6 member. As soon as it open, this carbon carries a positive charge. So you have to neutralize this positive. So this lone pair will be involved into delocalization. So there is a formation of double bond. As a result, the oxygen carries positive charge, right? The oxygen carries positive charge. So here I will write again positive charge. So same thing I will return, but here I will write a 6-member ring. Okay, so let us see same thing, but we'll convert into the 6-member ring. How? Look here. Now 1, 2, 3, 4, 5, and 6. So here we have to convert this 5-member into the 6-membered, but the oxygen is a part of ring. The oxygen is part of ring. Oxygen and the next carbon is your double bond O and H. Oxygen carries positive charge, right? So same thing I have written, right? And there is a removal of this O negative, right? And the last step is, that is a deprotonation, removal of a proton. So the sigma bond will open on the oxygen. Oxygen regain its lone pair. Previously it was having 1 lone pair. Now again it regain its lone pair, and you are getting corresponding, that is a 6-membered ring compound. So here you are having oxygen. Here you are having such type of compound, that is a C double bond O. Right? So in this way it will convert into gamma lactone ring. Right? So in this way it will convert into gamma lactone ring. So this is a simple mechanism, and even though we can write down number of examples here, if it is a 5-member, it becomes 6-member. Now next example, right? The next example, suppose if we are having a 6-member. Now I will take the different example. C double bond O. The reaction takes place in the presence of also cyclohexanone oxygenase, right? Oxygenase enzyme. Cyclohexanone oxygenase, ASE enzyme. Okay, and that is NADPH. It gives oxygen. Instead of using the reagent, we are using the enzyme, and as it convert cyclohexanone into corresponding one more increased size of ring, that is a corresponding lactone. So how to write the corresponding compound? It was a 6-member. Now you have to convert into the 7-member. Only we have to introduce oxygen atom. So it was CO. Here is the oxygen, and here we have to put one more carbon. Means it becomes, that is the 7-member. So I will put CO like this one. C double bond O. And what is the size of ring? Here is the alpha, here is a beta, here is a gamma, here is a delta, and E caprolactam. It is called as a E caprolactam. In mathematics, you all learn alpha, beta, gamma, delta, E like this one, E caprolactam, or simply say lactone. And if you are not able to write the numbering like this one, then simply say it is a lactone. So the conversion of a cyclohexanone into corresponding lactone. So the mechanism, just now you have learned the mechanism for the 5-membered. So in the same way, you have to write down the mechanism for the 7-membered. Similarly, also if suppose the size of ring is a 4-member, 4-member will convert into 5-member, right? So in this way, we can write such type of example, right? So in this way, we have seen the Baeyer Villiger oxidation reaction. So what is the use of Baeyer Villiger oxidation reaction? The name itself tells us that it is the oxidation reaction. You add oxygen on the, that is the that is the carbon compound, and it will convert into corresponding ester. Suppose if here instead of carbon compound, that is a ketone, if you are using aldehyde, if you are using aldehyde, I will write one more example. If you suppose next example is your next example R C double bond O, and here is H, right? Aldehyde. Now remember, when it is R and H, means it is a aldehyde. The reaction takes place in the presence of a per acid. So remember that the hydrogen undergo migration and it will convert into corresponding acid. So here you are having corresponding acid. So what you do, we have to undergo migration, that is a rearrangement, hydrogen on the oxygen. The mechanism is same, only I am going to add the examples. So in this way, you have seen the number of examples, right? So we have seen the open chain compound, also you have seen the cyclic compound. So let us see what you have done. We have seen the Baeyer Villiger oxidation reaction, in which the carbonyl compound will convert into corresponding ester in the presence of per acid. What are the per acids? We know the acid. Just you add oxygen, it becomes per acid. For example, formic acid, per formic acid, acetic acid, per acetic acid, per benzoic acid, or metachloroperbenzoic acid. And this is the mechanism of the reaction. There's an in general mechanism of the reaction. We can also write in particular only how to write down the R methyl or phenyl. If both alkyl group they are same, then we can migrate any R group. But if both alkyl group they are different, then we have to check the migratory aptitude, as we are going to shift on the O positive. So in this case, we have to check the R group which is found to be more nucleophilic in nature, or we can say more electron rich. With more electron rich, it will attack on the O positive. And we have seen the migratory aptitude also. These are some of the examples, right? So here the phenyl, and here is a paramethoxy benzene nucleus. This is more nucleophilic, that's why it will attack. These are some examples of per acid, per acetic acid, per formic acid, then trifluoroporacetic acid, right? This is the migratory aptitude. Even though if you take such type of example, cyclic compound, just you have to introduce the oxygen atom and you can get corresponding product. Okay, so in this way we have seen the mechanism of this reaction, right? And if there is R and H, in that case the hydrogen will undergo migration and you are getting corresponding acid. So aldehyde to acid can be undergo conversion by using per acid, and the name of reaction is the Baeyer Villiger oxidation reaction. Baeyer Villiger oxidation reaction. Okay, so in this way we have seen the next third rearrangement reaction, that is called as Baeyer Villiger oxidation or rearrangement reaction. In doubt, you may ask, If in doubt, you may ask. We can refer the book. There is the Manali publication book or the Nirali publication book. We can use the reaction, reagents and rearrangement by Sanyal and Sanyal. Try to write down one generalization and make it in particular. And remember which step is a rearrangement step, where you have to undergo rearrangement, where you have to undergo migration. What is starting compound, what is the product, and what is the reagent. So reagent is a very simple, that is the per acid, and we should know how to write the per acid. Okay, end out? No. Then I think we should stop here. And tomorrow again by 8:30 we'll start our lecture and we'll take a new rearrangement reaction. And thanks to all. Thank you.
Thank you, sir.
Thank you, sir.
Thank you. Thanks.
Thank you, sir.
Thanks to all.